Welcome back to Reconstructing Gravity, Chapter 2, called G-Rocket. And we're going to look at some of the basics of gravitation and acceleration and show that they're very similar but not exactly the same. First, some basics. Mass is not the same as weight. Mass is kind of the amount of stuff, the amount of material. Weight is a force. So on a particular planet or a particular situation, mass will have some weight. It will take some force to keep that mass from falling. So, but to be weightless is not to be massless, okay? Newton said force equals mass times acceleration, and weight, which is also a force, equals mass times g. Weight equals mass times g, where g is the acceleration due to gravity. That's what it's called. G is a local parameter, depends on the planet. So g on the moon is about 1/6 of the g, little g, on Earth. So a person weighs about 1/6 as much on the moon as they weigh on Earth. But their mass is the same. Mass is a constant. Per Newton, F equals ma. So if you want to get, if there's only one force acting on a mass, you'll get an acceleration from that force if the force is maintained. But if you want to get the same acceleration out of a larger mass, you'll have to have a larger force to get the same acceleration. And acceleration is a rate of change of velocity. So you can see in the table, as time goes forward, if you have a constant acceleration, the velocity will just increase steadily, 2, 4, 6, 8, 10. But the position increases on a power of 2, like a parabola, 1, 4, 9, 16, 25, 36. So if you're starting from a zero position at zero time and zero velocity, the position is 1/2 at squared. So as you can see in the chart, the position is a parabola, whereas the velocity just increases in a straight line. So what is weightlessness? Zero G is kind of a misnomer. It doesn't really mean that there's no gravity acting. Just really it should be called zero weight. Astronauts in orbit are in free fall, and everything, their ship they're in and everything inside it is in free fall. Gravity is still acting on that jar of peanut butter. For a mass to travel in a circle, there needs to be a centripetal force. So if you took a bucket of sand of mass m and tied it to a rope of length r and swung it around in a circle at speed v, it would require force F to keep it going in a circle. And the equation for that force is mv squared over r. And since F equals ma, that means the centripetal acceleration is v squared over r. When in orbit, gravity is the centripetal force, the force that acts towards the center. The ship, the astronauts, and the peanut butter jar are all in free fall, falling around the Earth. The speed v has to be just right to keep them in a circular orbit. And you see that F equals mg equals mv squared over r, so you can see the m cancels out. Every mass gets treated exactly the same way. Every mass has the same acceleration. And that acceleration g of gravity equals v squared over r. So for a given height and a given gravity at that height, certain v is required to stay in a circular orbit. Now, when we say the word free fall, we often think of skydiving. And an interesting thing happens in skydiving. You can look at the graph. The acceleration due to gravity is a constant force, or almost constant, because gravity gets a little stronger as you get closer to the Earth, but it's relatively constant. So the velocity, as you see in the graph, the yellow line starts out steadily increasing. But as the velocity gets higher, the drag force starts to become larger, and eventually the drag force equals the gravitational force, and at that point, the speed levels off. It becomes, you stop falling faster and faster and just keep falling at the same speed. It's called terminal velocity. Now, obviously, if you're just standing on the Earth, you're not in free fall. But the reason you're not in free fall is because there's an upward force that equals the downward force. Gravity's acting on you, but there's an upward force on your feet that's an equal amount. And you can see in English, we would call a 150-pound person. That's a weight, but the mass is actually 68 kilograms. The g, the acceleration due to gravity, would be 9.8 meters per second if in free fall. And m times g is the weight, is 666.4 newtons. Newtons is the unit of force in the metric system. So 1 newton of force is the force required to accelerate 1 kilogram at 1 meter per second every second. And 9.8 newtons of force is the force required to hold 1 kilogram against the acceleration of Earth, standing on Earth. Now, when Einstein started thinking about gravity, he did some thought experiments. First, I think he thought about elevators. You know, that feeling you get when an elevator starts to move upward, that you're just a little heavier. And then when you get up to the floor and it slows down, you feel a little bit lighter. And he said, well, that's just like gravity. And somehow he imagined in 1905 that if you were in an accelerating rocket ship in deep space, accelerating just the right amount, it could feel very much the same as gravity, and you wouldn't be able to tell the difference. If you're in such a ship and it was accelerating, that acceleration would produce a force acting on you, as it would have to accelerate you. I imagine that to control this, you'd set up your throttle of your rocket engine such that when you put a 1 kilogram mass on top of the scale, it would have to be a spring scale, not a balance scale, put a 1 kilogram on top of your scale and set your throttle so that it reads 9.8 newtons. If the weight is less than 9.8 newtons on the scale, then you'd want to accelerate the ship more. If the weight was more than 9.8 newtons, then you'd want to back off on the throttle, and you could have an automatic system that would maintain that constant acceleration of 9.8 meters per second, and it would feel very much like standing on Earth. Or if you wanted to work in pounds, you could take a mass that weighed 1 pound on Earth, put it on the scale, and set the throttle to read 1 pound. You'd be creating the same acceleration that would produce normal weights in your rocket ship, Earth normal weights. This G rocket would be a very human healthy way to travel, and you would get up to some very high speeds before too long if you could continually produce the sufficient thrust to maintain that acceleration. You'd need some really advanced rocketry. But would the gravity be exactly like that on Earth? Not exactly. No, it wouldn't. The subtle differences between gravity in this kind of rocket ship and gravity on Earth became part of Einstein's General Relativity model. The differences are very subtle. First, on the ship, if you drop 2 balls side by side, they would drop in parallel lines. Not so on Earth. On Earth, balls dropped side by side fall together. They fall towards the center of the Earth. Very, very subtle effect. You wouldn't really notice it, but it's the truth. Balls don't fall in parallel lines, they fall in radial lines towards the center of the Earth. And on the ship, balls dropped at the same exact time from different heights would both have the same apparent acceleration, and they would maintain a constant distance from each other as they dropped. Not so on Earth. Why? Because, per Newton, the closer you are to the center of the Earth, the larger the gravitational force. So the ball that's dropped from a lower height would always be moving at a slightly faster speed than the ball that was dropped from a higher distance, even though they were dropped at the same time. So the balls would actually separate a little bit as they fell. Very, very subtle. But these two subtle differences turn out to be really significant in Einstein's work, and they'll have some meaning for us too here. We'll come back to using those two subtle issues later in this video series. But I'm going to wrap it up here, and in the next video, we'll come back to this rocket ship for some other things. And here's the hint. We're going to be looking at clocks in this ship and bring in the time skewing concepts from our constructive model of special relativity. If you haven't done so, be sure to check out my earlier videos on special relativity and the series called Reconstructing Relativity. You're going to need to have those basics for what we get into pretty soon here in gravity. But thanks for watching this one. Please like and subscribe. Leave me a comment. I'll get back to you. And as usual, find some music and catch you next time.